Okay, few things before we even start hypothesis testing. Fundamentals of statistics. I'm not going to get into mean, median, mode, all that stuff, but the basics that we need to know in order to understand hypothesis testing, because this class primarily focuses on hypothesis testing. Reason being, psychology revolves around testing hypotheses. So does social science. So does natural sciences. We want to make a hypothesis, we want to test it using that. So, I guess I'll start with my picture. Curly box doesn't matter. What is that bigger set called?
Population.
Very good. What's your name?
Savannah.
Savannah. Population. That
Sample.
sample. Emily. Okay. Oh, I'll eventually remember names, but don't switch spots because I have photographic memory. I can associate based on what I see. The moment you switch, I'm done. Population, sample. Our objective is to understand the population, just one, or multiple populations. Compare populations. So we're going to start with one population here, but the very first test, hypothesis test that we will be doing will compare two. So the object of interest is the population, and in order to study the population, we get a sample that is randomly selected from the population. Why should it be randomly selected? Why random?
That's not biased.
It's very good. Fancy word, bias, but you know, felicity. We don't want bias. For instance, if you are testing a drug that is effective in reducing anxiety, it would be silly for me to include a good amount of people who are not anxious at all. Correct? So they are naturally perfectly fine. And you're giving the drug to those people, and you're going to claim, oh, the drug is amazing. Well, they don't have anxiety to begin with. By randomly sampling a population, we can avoid that bias. So whatever sample that you collect has to be random. If it's reasonable or even possible for me to study the entire population? No, because going back to my anxiety and drug example, there is no way that I can look at every single individual that has anxiety. Some may not even know, some probably don't want to disclose. So in sciences, we base our conclusions using a sample. And when random, when the experiment is done properly, whatever inferences that we can make using a sample can be extended to a population. Yes? Let's say I did a study today and I concluded that the drug is effective. Is that set in stone? Is my conclusion Perfect. Well, what do you
Sarah,
Sarah, why not?
things change.
Things change. For example, another researcher somewhere across the world might do an experiment and claim that their design is better, and according to their design, they conclude that the drug is not effective. Now you may say, well, that's contradicting stuff. Well, that's why we have a bunch of knowledgeable people. That's why we have peer review. Bunch of peers look at the conclusion, and if they determine that the second experiment is more valid than the first, I have to go with what the second experiment states. So, sure, I have a sample. I extend the conclusion that I get from the sample to a population. Doesn't mean that it is the truth. Good, keep that in mind. So the truth can be changed, or I shouldn't say can be changed, could be changed because of a different sample, different experiment. Naturally, that would bring another question. What is the purpose of statistics then? If things keep on changing, if you can't find the truth, why do we waste time? Thoughts?
To estimate the truth.
To estimate the truth, and that estimation could change, right? My question is, if the estimate keeps on changing, hypothetically speaking, what is the point of doing it over and over? There is.
To see trends. See trends.
What's your name?
Eden.
Eden, okay. To see trends, I'm going to paraphrase that word trends and use consistency instead. Being consistent is a trend. Let's say you repeat this experiment 1,000 times, and about 927 times you keep reaching the same conclusion that the drug is effective. At that point, I can be pretty sure to a certain degree that the drug is effective. Do you agree? So if there is a truth, then no matter how many random samples you come up with, you would consistently come to the same conclusion. Okay? That is the fundamental principle behind statistics. Do we understand this part? Yes. Okay. The next step is a few things that we use to study the population. Let's see. Parameter. Who wants to go? What is a parameter?
Maybe if they had like test scores that fell in between.
Test scores, okay. What is your name?
Riley.
Riley, okay. I'm going to write that over here. We will get to this. I don't want to bring that to there. Anything else?
This is going back to the parameter, it's the exact amount of something.
Exact amount of something. What is that something? That's my question.
Jasmine,
Okay.
I feel like the exact number of successes.
Exact number of successes. Jasmine's being all fancy. Exact number of successes in my example for the drug being effective. What is the success? Right?
People that don't have anxiety.
I'm testing a drug.
Don't feel it.
That's it.
Anxiety.
Oh,
Don't feel anxiety after taking the drug. Yes? So I have 1,000 people. 927 say that it reduced anxiety. 73 concluded did nothing. Good. And if I asked you, well, what percent of people who took the drug found it to be effective, what would your answer be? I'm hearing sounds, but I don't know where it's coming from.
92.7.
92.7%. How did you compute that, Felicity?
That's quite,
Well, then others know too. So,
but instead of being out of 100 or 1,000, so you know you need to move to the next 1.3 places.
okay, what Felicity is trying to explain is 927 divided by 1,000. Yes. Point 927, 92.7%. The percent of people who found the drug to be effective simply has a fancy name in statistics. Which is proportion. Proportion of people who found the drug to be effective is 0.97. If you are explaining this to someone who is not very knowledgeable in statistics, I don't want to use this fancy word. You can simply say the percent of people. Easy to understand. So proportion is a parameter. Letter is P. The next parameter that we often use is mean. Recently took 2023, you should know what is the notation for mean population. Think of a cat. Mu. Good. That's how I communicate with my cat. I have developed a unique language, just like Morse code, single mu followed by 3 mu's. They respond. Next one. Variance. Variance is used to study variability, and that is denoted by sigma squared. All of these are notations that we use to explain a parameter. But the parameter belongs to the population. I think it's Cyrus here. Savannah. See, I knew it started with S and ended with H. Eventually. Savannah earlier mentioned estimated amount. When we say estimate or estimated, it is coming from a sample. You change the sample, the estimate probably is going to change. So the estimated values using this because the book uses it, it'll show up in the homework. So you need to know the distinction between the two. So the parameter is not the same as an estimate that you compute from the sample. to differentiate a parameter from a statistic, we simply put a hat on top of it. So if I use P, I'm referring to the population parameter. If I put a hat on top of it, it is an estimate. So naturally, how would you write here? Say X bar. And let's say, okay, but I don't want bars, I want the hat. How would you write it?
Why?
Why hat? Where is Y coming from?
I'm thinking that's.
So that's from regression. You're thinking of regression.
Yeah.
So B hat, mu hat. So Elizabeth said X bar because X bar is a common notation that people use to refer to the sample mean. Now, take a guess. Sigma squared. Hat squared. Some use this. Or people simply use S squared. Good. I'll put a remark here. Even though we test for variance, in practice, standard deviation is more useful. So standard deviation is simply the square root of variance. So in the parameter side, if I want to denote the standard deviation, I would simply put sigma. If I want to refer to the statistic, what will I write here? Notation. S or
Sigma.
sigma hat. Oops. Good. Call it as an important aspect. All of statistics deals with this particular one thing. Let's see, we should have done it in 2023. I guess we'll do a word game. Starts with the letter D, ends with the letter N. Okay, algebra.
The P.
D. Okay, how about this? And I'll do that.
Deviation.
Okay, deviation is fine. I'll change something else too.
Distribution.
Distribution. So the most important thing, or I shouldn't say most, one of the most important aspects in statistics is distribution. Why distributions or help us find something that's important in statistics as well. Before we get to that quantity, one can compute using a distribution. Can you think of a distribution? Which one comes to your mind? Easy.
Normal.
Normal. So what does it look like? A bell. A bell curve. This is something we will see a lot. So when we show a bell curve, we are referring to a distribution. With me so far? Going back to 2023 again. Bell curve. Good. Area under the bell curve. Yes. What did it correspond to? Every time you found the area under a bell curve, what did you compute? So the z-score, you call it z, I call it z. My way is better because you can't confuse it with c, right? Try talking to someone, you know, 1-800, they confused. But when you say z, that's all. That would be a score that you have. My question is, if you find that area what would that refer to?
T square. The proportion. The proportion.
Proportion, okay. That is the correct answer. But I don't want you to confuse this with this. So let's use a different word, even though they are.
Does it have to do with the levels or?
We are getting there slowly. Do we have to do the word game again? Start with the letter P.
Probability.
Probability. It refers to probability. No matter what distribution you have, when you find the area under the curve, you are finding probability. Now, what Savannah mentioned as z-score, Amelia, did you say t-score? Z-score, t-score, just a value, all of those belong on the x-axis. So you need a score to determine probability. So if, for instance, z is 1.96, we can find the probability above 1.96. Good. Jasmine brought this up. Do you want to repeat what you said, Lavender?
Alpha levels.
Alpha levels. When we get to hypothesis testing, two important quantities that we will use time and time again would be alpha and p-bar. Both of them refer to probabilities, and they are computed using the area under the curve. With me. This is something you may or may not have done in 2023, but I want to mention here because we will use it later. Another distribution curve. Does it have a skew? What type, Renee?
Right.
Skew right. So this is a right skew distribution. We will see right skew distributions later. No matter what distribution you have, the idea is exactly the same. You need a score of some sort, score or a raw value from the data in order to find the error. No score implies no error. Good, so don't forget that part.